My name is Tuomas Hakamäki, and in this presentation, I will talk about thermal and structural modeling of CLT-slab in natural fire, with the main focus on comparison to test results. So quickly about me first. So I'm Tuomas Hakamäki. I'm working as a structural fire engineer for Jensen Hughes, Finland, and I'm located in Helsinki. This presentation is based on my master's thesis, which was called Fire Resistance of CLT Horizontal Structure in a Natural Fire. And I graduated as a structural engineering from Tampere University. The key content of that master's thesis research was the differences in fire design of CLT horizontal structure between current design guidelines and the forthcoming next generation Aero code. And these next bolded contents are what I'm talking about today. So the introduction, definition, and application of the duration of heating phase, or DHP concept. Then I'll present the fire test of the CLT-slab, which we conducted, and then a modeling of the fire test with SAFIR and comparing the results of the fire test and the model. So first about the DHP concept, in which we construct this fire curve, which is a basically simplified version of the Eurocode 1 parametric fire curve. In this curve, we set the gamma factor to 1 to minimize the variables. So there is only that duration of the heating variable. This results in a standardized parametric fire curve, which has the heating phase very similar to the standard fire. And after the heating phase, we have the cooling phase, which is happening around 10 degrees Celsius per minute. With this fire curve, it is proposed to determine burnout resistance, or B classification, for the structure, indicating the longest duration of the heating phase, after which the structure would still probably withstand the entire cooling phase, maintaining its load-bearing capacity. So if we have this B rating threshold and the heating phase would be shorter than that, then the structure would likely to survive the fire considering the cooling phase. On the other hand, if the heating phase would exceed the B rating, then the structure would likely to collapse during or after the cooling phase of the fire. And the B classification is not proposed to replace any existing classification, but to use as an additional informative classification alongside the R classification, for example, R60 B25. And this is a great figure about the concept, illustrating that when we have the standard fire curve in the 60 minutes time, if the structure is rated R60, we would assume that the structure will collapse at that point. Then the solid black line represents the B classification, meaning if the heating phase is that or shorter than that, the structure would withstand the fire. And if the heating phase would exceed that threshold, then there would probably be a failure during the cooling or even after the cooling. So the test specimen we had was the CLT-slab from Crossland, Kuhmo. Its nominal dimensions was 40, 20, 20, 20, and 40, with the total height of the cross section 140 millimeters, the width of 500 millimeters, and the span was 3.77 meters. And the adhesive used in the cross section was polyurethane based, so in theoretically it was prone to delamination. The fire test was carried out at the fire laboratory at Tampere University. About the loading conditions, we estimated the load value at which the structure would collapse during its cooling phase. The used loading was 20.6 kilonewtons, which corresponds to approximately 28% of its load ratio, so the maximum capacity calculated at normal strength. The estimation was based on jarring according to the next generation Eurocode 5 and the evaluation and application of the expected value of bending strength. So the estimated bending strength was somewhat uncertain due to the large variability within timber products, and the final used bending strength was estimated to be 31.2 megapascals, which is slightly higher than what the Eurocode 5 would propose to be used. For the fire scenario, the used fire curve was, according to DHP concept, DHP 35 fire curve, which has the heating phase of 35 minutes, followed by the cooling phase, constructed with the parametric compartment fire curve, where the gamma factor is set to 1. In the figure, you can see that the heating phase is very similar to the standard fire curve, and then followed by the cooling phase. So the results, the fire curve in the fire test is presented here. So the fire curve was matched relatively well, and the cooling was a little bit slower than planned because some heat inevitably remained in the furnace. And this orange curve is the one used in SAFIR modeling. About the thermal modeling of the CLT-slab, material model wood EC5 was used, and parameters for that was taken from the measurements of the specimen before the fire test. So in the cross section, 2 materials were defined: CLT0, which are the load-bearing lamellas, and CLT90, which are the non-load-bearing lamellas. But in the thermal modeling, the thermal properties are similar to in all of these, or both of these materials. The cross section is identical to what was fire tested, and the section was discretized to 0.5 millimeter thick beam elements. About structural modeling, the used material model for the load-bearing lamellas, CLT0s, were wood EC5, and the material model for the non-load-bearing lamellas was insulation, so it did not have any ability to carry any stress. The model was discretized to approximately 10 millimeter long beam elements, and there were 2 node loads because there was a distribution beam for the loading, so the total load was that 20.6 kilonewtons. And in top of that, there was a distributed load from self-weight and the rest of the test setup. So this is the main result of the fire test and the SAFIR modeling. So collapse of the structure. In fire test, we had collapse at 263 minutes, so almost 4.5 hours, which is almost 4 hours after the start of the cooling phase. In SAFIR, on the other hand, we had collapse at 91 minutes, so very notably a shorter amount of load-bearing capacity there. But on the note, we have that the strength in the model was estimated because we did not have an exact value for the strength values of the slab. For temperature distribution in the fire test, the temperature were measured from 3 points per lamella, and the average of these is presented below with the solid lines. And for reference, the results from SAFIR or diamond is presented with the dashed lines. So the shapes of the curves are very similar, but the SAFIR gives somewhat greater temperatures than what we measure from the fire test. If we strictly look the heating phase, then the curves are very, very similar to each other in these two methods. About charring depth, the average charring depth measured from the fire test from 20 points. So average of these 20 points was 31 millimeters. And here you can see the snips from SAFIR or diamond that we have in 35 minutes, which was, of course, the start of the cooling phase. Was around that was around 22, 23 millimeters of charring, and eventually at 61 minutes, the maximum depth of the 300 isotherm was 30 millimeters approximately. So the results in these was very similar with the charring. No delamination occurred under the DHP 35 curve, as the exposure just wasn't enough for the delamination to happen. About deflection, the deflection was measured at 3 points, the midpoint of the span and the areas near the load distribution beam. So figure on top presents the deflection from the fire test, where we can see that we have increasing deflection throughout the entire test from 0 to the 263 minutes, and it is somewhat linear, or there are some linear phases in that deflection there. And the figure below presents the deflection of the fire test versus the SAFIR results, where the fire tests are presented with solid line and SAFIR results with dashed line. And it's notable here that with the fire test, the maximum deflection value was 232 millimeters, whereas the SAFIR only calculated at it to 104 millimeters. The sudden increase of deflection was noted in SAFIR results just before the 60 minutes mark, and it was assessed that the first lamella was lost then, but the cross section had enough strength to maintain the load bearing at this point still. So as the deflection in SAFIR reached just 45% of the result from the test, the strength was increased to assess that parameter's impact on the structural capacity. So the bending strength was raised stepwise by 1 megapascal until a clearer relationship with the collapse time appeared. So from 31 to 34 megapascals, we gained 15 minutes of additional capacity. Then with 1 megapascal addition, we had about 30 minutes, and then with 36.2 megapascal, the structure did not collapse at all, with the maximum deflection reached still just 124 millimeters. So for the conclusions, we can say that the horizontal CLT structure may collapse during significantly prolonged cooling phase due to the delayed effect of the heat wave. So with 35 minutes of the heating phase, the collapse happened 228 minutes after the start of cooling. SAFIR is seen very effective in these kinds of analyses, even though the results in this research were notably conservative. So the simulations demonstrate significant savings in time and cost for the, of course, the amount of fire tests to assess these kinds of structures would be very costing in time and money, of course. The material model wood EC5 does not appear to be fully suitable for the CLT slab, as it restricts the plastic behavior, resulting in less ductility than observed in the fire test, which of course were observed to be very ductile, the test specimen there. So the test specimen failed under the DHP 35 fire curve, meaning that the burnout resistance, or the B rating according to the DHP concept, is no greater than B34. This was then numerically iterated with SAFIR to a B rating of B25, which of course is somewhat conservative in this case, what was presented in the deflection curves, for example. For this CLT structure at the given load level, the B classification was about 53 to 73 of its R classification, which was calculated according to the next generation Eurocode to be R47 with these loading conditions. So the B classification would be between 25 to 35 minutes, meaning that if the heating phase of a fire would exceed that, then the structure would probably collapse somewhere in the cooling phase. Then to wrap this up, a few thoughts. The load value was estimated to be just a bit too small, so we were probably quite close to a situation where the structure would not have collapsed at all, as the deflection rate at the end was as low as 1.5 millimeters per 5 minutes. Well, in the end, we had that collapse what we were looking for. So maybe it was not too small, but yeah, it was kind of painful to watch the the slab and think that it would not collapse at all. SAFIR did not reach the equilibrium when the deflection was at 104 millimeters, whereas the deflection of the specimen was more than twice as large. And this, I think, is very simple problem to handle, as it probably is as simple as trying some different material model for the CLT in structural analysis, and that should probably give much better results. And of course, these results are slightly limited due to the fact that there was only one CLT fire test conducted. So, of course, more fire tests, including varying strengths and load levels, are needed to improve the reliability and reduce the errors. Yes, that is my presentation. Thank you. Thank you all for listening.